Okay, so in the previous video we talked about or were introduced to this idea of powers and exponents. Today we're going to look at a whole bunch of properties of these powers. Now as far as what you need to know, you need to be familiar with the name of these and just in general how we apply these or what these postulates are and how we use them. So for each of these I'll show you the general form, and then we'll have some examples as well to illustrate what each postulate is talking, or each theorem is talking about. So let's look at this first one. So this first one is called the product of powers postulate, meaning that if I multiply two numbers whose bases are the same, remember that was a phrase we learned in the previous video. The bases, remember, are the numbers sitting on the ground. So when the bases are the same and we're multiplying, we add the exponents. So the base remains the same and the exponents we add together. So for example, let's say if I have x cubed times x to the 4th. My answer is not x to the 12th. We don't multiply the exponents, we add the exponents. 3 plus 4 is 7. Now you might ask, well, why is it that we add the exponents? Well, let's look. If I had x cubed, that's the same as x times x times x. If I multiply that times x to the 4th, well, x to the 4th is x times x times x times x. Notice I have 1, 2, 3, 4, 5, 6, 7 x's being multiplied by each other, giving us x to the 7th as my answer. So x cubed times x to the 4th would be x to the 7th. Faster way was, basically that's what these postulates are doing, coming up with a faster way to simplify these. So we would add the exponents to get x to the 7th. So the next one. The quotient of powers theorem. Well, let's talk about this for a second. With the product of powers postulate, that said that when we multiplied and the bases are the same, we added the exponents. Well, if you think about quotient as dividing, that's the opposite of multiplication. So result is going to be the opposite here. Instead of adding the exponents, we're going to subtract the exponents. Why, you might ask? Well, let's look at an example. Let's say if I have x to the 8th power divided by x to the 6th power. What that means is I would have 8 x's on top. 1, 2, 3, 4, 5, 6, 7, 8. And I would have 6 x's on the bottom. 1, 2, 3, 4, 5, 6. And we would cancel out 6 from the top and 6 from the bottom, leaving me with 2. So x to the 8th divided by x to 6 would be x squared. A faster way to do that, though, instead of having to draw it all out to illustrate it, all we have to do is subtract the exponents. 8 minus 6 is 2. Let's talk about this now. The power of a product postulate means that, let's say if I have some things multiplied inside of parentheses and an exponent outside the parentheses. This exponent we would distribute, so it would get applied to both the a and the b. So for example, say if I have 3x cubed, or 3x, the whole thing being cubed. It doesn't mean just the x gets cubed, that means everything gets cubed. So the answer would be 3 cubed times x cubed, which is, well, 3 cubed is 27, x cubed. So 3x in parentheses, the whole thing being cubed, would be 27x cubed. So whatever is outside the parentheses gets applied to everything inside the parentheses, whether you're multiplying or dividing. That's what the power of a quotient theorem tells us. So here we're dividing, same rules apply. So if I have a divided by b to the nth power, it would simplify to be a to the nth over b to the nth. For example, if I have two-thirds and we're squaring that, that means both the 2 and the 3 get squared. So 2 squared is 4, and 3 squared is 9. So my answer would be 4/9. We do have 2 more, even though I forgot to put this one in our notes. So you're going to want to add this power of a power postulate. So even though our notes say that there's only 1 more left, there's actually 2 more that we're going to look at. But the next one is kind of a basic one, but it's one that people nonetheless end up messing up on. If we have any number raised to the 0 power, it's not 0. If we have any number, variable, whatever it is, raised to the 0 power, your answer is always going to be 1. Please, please, please don't make this mistake. B to the 0 power is always equal to 1. 3 to the 0 power is 1. Pi to the 0 power is 1. X to the 0 power is 1. Anything raised to the 0 power is 1. So here's where that comes in handy. Let's say if I have 3 to the 7th over 3 to the 7th. Well, we just talked about the fact that if the bases are the same and we're dividing, we can subtract the exponents. That was the quotient of powers theorem. Well, 7 minus 7 is 0. So now I just found out that 3 to the 0 power is 1. Okay, let's look at this last one again. Make sure you write this one down. Power of a power postulate. What if we have a situation like this, where we have something that has an exponent, and that's also raised to an exponent? This will be the one time where we do multiply the exponents. So in other words, if I have 2x, or let's just say this is a y, 2y squared, and that's being cubed. Well, from what we talked about up above, for the power of a product postulate, tells me that I would cube everything inside of here, so this would be 2 cubed. And y, we multiply the 2 times the 3. Well, 2 cubed is 8. 2 times 3 is 6, so we'd have 8y to the 6 would be your answer. Okay, so again, for this lesson, you want to make sure that you have all these written down. You want to make sure you understand these, so then you can apply them to some situations here. That's what we're going to do next. Here they say to solve 14 cubed times 14 to the what power equals 14 to the 10th power. So for this one, notice how the bases are the same. So this is a product of a powers postulate because we're multiplying. So we're going to add the exponents. So I want to figure out, if I add the exponents, what would x have to be in order for this to be a true statement? Well, 14 would add the 3 and the x together, add those exponents, and it's going to equal 14 to the 10th. So what plus 3 would equal 10? Would be 7, so x would equal 7. Let's look at the next one. Take a second to look at that and figure out what x would be. Did you get x is equal to 8? If you did it right, because trying to figure out, since the bases are the same, we're going to add the exponents. So trying to figure out what x would have to be to get 12 as an exponent. Well, 4 plus 8 is 12. If you didn't know that, you'd set it up as an equation and subtract 4 from both sides. And like I said, you get x equals 8. Okay, let's look at this one. Again, I forgot something here. It says, how many zeros are at the end of the number 2 to the 6 times 5 to the 6 times 17 when written in base 10? It's written in base 10. That just means that you're going to be writing it not in scientific notation. We're going to, if we were to write this out, what would your answer be? How many zeros would be at the end of this? Well, if you notice, they have the same exponents. So we're going to go backwards from one of our theorems here. The power of a product postulate. If you notice with this one, a times b to the nth power is the same as a to the nth times b to the nth power. What we have in this situation is they give us a problem like this, so we're going to rewrite it to look like that. How might that help? Well, you'll see. So again, this 2 to the 6 times 5 to the 6, and write this as 2 times 5 to the 6th power times 17. Well, 10 to the 6 times 17 means that we would end up having 17 with 6 zeros, followed by 6 zeros. So this 10 to the 6th power tells me that there's going to be 6 zeros. Let's look at the next one. 5 times 2, I can put inside of the parentheses and the fifth power outside of there. 5 times 2 is 10, so we have 10 to the fifth times 32. So how many zeros would we have? Hopefully you thought of 5 zeros. This 10 to the fifth would be a 1 followed by 5 zeros times 32 would end up being 3,200,000. So we've got a couple of other examples. Let's look at this one. This multiple choice test is 3 pages long. Each page is 5 questions. Each question has C possible choices. How many different ways can you complete the test if you leave no answer blank? Let's think about this for a second. There's 3 pages. Each page has 15 questions. So that means there's 15 questions total. Trying to figure out how many different ways can you complete the test if you leave no answer blank. So each question has C possible choices. So here's how you set this up. We're going to write this as C to the 15th power because easy way to do these type of problems when we're dealing with probability is your base represents the number of choices. The exponent represents how many repetitions you have. You have 15 repetitions. There's 15 questions. We don't know how many choices each question has. Maybe there's 2. Maybe it's true or false. Maybe it's multiple choice with, well, I guess it does tell us it's multiple choice. They don't tell us how many choices, though, each question has. If each question had 3 choices, the number of different ways you could complete it would be 3 to the 15th power. If each question had 4 choices, it'd be 4 to the 15th power, and so on. So again, the base here, if you want to make note of that, that might not be a bad idea. The base represents the number of choices. The exponent represents the number of repetition. So here we have a multiple choice test, English quiz I should say. That's 2 pages long and each page has 6 questions, so there's 12 questions total. Each question has C possible choices. How many different ways can you complete the quiz if you leave no answer blank? It would be C to the 12th power because we have C choices for each question and 12 repetitions of the same question, same type of question, so it would be C to the 12th. Let's look at another story problem. This one here, it says, in 2005, astronomers using the Hubble Space Telescope discovered 2 tiny moons named Hydra and Nix orbiting Pluto. Oops. Hydra's mass is believed to be between, actually let's change this, there's a typo. We're going to change it to be 2.4 times 10 to the 18th. Okay, so Hydra's mass is believed to be 2.4 times 10 to the 18th. And in kilograms, the mass of Earth's moon is 7.35 times 10 to the 22nd kilograms. How many times as massive is Earth's moon as Hydra? So we're going to take the Earth's moon divided by Hydra's mass, and that'll tell us how many times larger our moon is than Pluto's moon, Hydra. So to figure that out, again, our moon's mass is 7.35 times 10 to the 22nd kilograms. Hydra is 2.4 times 10 to the 18th. So remember in the previous, or one of the previous rules that we talked about was that when the bases are the same, we subtract the exponents. So that's what we have here. We have 10 to the 22nd divided by 10 to the 18th. So the bases are the same, so we're going to subtract the exponents. 22 minus 18 is 3. I'm sorry, 4. Getting ahead of myself. 10 to the 4th. To figure out the other part, these bases are not the same, so we just divide those normally. If you take 7.35 divided by 2.4, you get approximately 3, so we'll just write that as 3 times 10 to the 4th. And that would be your answer. Why don't you guys try this next one on your own? The mass of Earth, so this is actually talking about our planet, is about 5.9 times 10 to the 24th power, while the mass of Jupiter is about 1.9 times 10 to the 27 kilograms. The mass of Jupiter is about how many times the mass of Earth? So we want to figure out how many times larger Jupiter is. So we're going to figure that out by taking Jupiter's mass divided by Earth's mass. So why don't you guys work that out, and so pause the video and hit play when you're ready to check your answer. Okay, let's see how you did. You should have taken 1.9 times 10 to the 27th power divided by 5.9 times 10 to the 24th power. Again, here we have the bases being the same, so we're going to subtract the exponents. So it gives me 10 cubed. And 1.9 divided by 5.9 is approximately 0.3. So we have 0.3 times 10 cubed, which, if we rewrite that, this tells me I'm going to move the decimal place to the right 3 places, so my answer would be 300 times larger. So Jupiter is 300 times larger approximately than Earth. Let's see how we can apply that to this problem here. It says farmers often use circular irrigators on square plots of land, leaving the regions at the corners unirrigated. How does a percentage of irrigated land depend on the radius of the circle? Okay, so we want to see how does a percentage of irrigated land depend on the radius of the circle. So let's have a diagram. Close enough. So if you think about how to find the area of a circle, the area of a circle is pi times a radius squared. And we also have a square happening here. So the area of a the area of a square is going to be just this, whatever the side is squared. So if this is S and this is S, the area of a square is S squared. Well, how can we tie these two together for this one problem? Well, let's look at the circle here. If this circle has a radius of r, that means that the square, each side, is a length of 2r. Remember, the radius is the same any way you cut it. So anywhere you look on the circle, the distance from the center to a point on that circle is going to be r. So from the center over to the left side here would be r as well. So we have one end of the square to the other end of the square is 2r. So to figure out how many times larger one is, we're always going to take the easy way to remember to figure this out as a percent. You always take the part divided by the whole amount. Well, the part is the circular area, so that's going to be pi r squared. The whole amount is the square, which is 2r times 2r, or 4r squared. Simplifying this, r squared divided by r squared gives us pi divided by 4, which as a decimal is 0.785. It asks us how does the percentage of irrigated land depend on the radius of the circle, so we need to change this to a percent. So we would say 78.5% of the land is irrigated. So that means about 21.5% of the land goes unirrigated. It's not getting water. Okay, now if you remember that trick of taking the part divided by the whole, that'll help you when we're trying to find percent. So let's look at this one. A cylindrical can containing 3 tennis balls fits tightly in a rectangular box as shown. What percent of the volume of the box is taken up by the cylinder? Now I'd give you these formulas so you don't have to worry about the fact that it's not given to you here. But the volume of a cylinder is going to be pi times a radius squared times a height. That's what we have in the middle. And that cylinder is contained inside of a rectangular box, a rectangular prism. And the volume, let's say the volume of a box, be easy, would be to just say that it's the area of the base, which is, they did a poor job giving us a diagram here. This is a square for a base, so it'd be this s squared times the height. Well, if you think about it, the base, this circle here has a radius of r, and just like the previous example then, our square is going to have each side being 2r. So the volume of the box is going to be 2r times 2r, which is 4r squared times the height. The volume of the cylinder is going to be pi r squared times the height. Well, the heights cancel out, the r squareds cancel out, and we're left with the same thing that we had before, which is pi divided by 4, which is going to give us 78.5%. Is going to be used or filled. Okay, so those last two examples are kind of tricky, but we just want to emphasize the fact that the majority of this lesson, the most important part of this lesson, is going to be these first couple of examples of knowing how to apply all of these theorems and all of these postulates to different situations. So with that, good luck on your assignment.